Next up on our agenda, we have Luis Rodriguez of JHU APL here presenting on the DART Flight Software Imager Application Testing Campaign. Luis, thanks so much for being here, and it's all yours.
Thank you, Brandon, and good morning and good afternoon to everybody across the world. So today I kind of wanted to take these next 25 minutes to discuss the DART Flight Software Imager Application Testing Campaign. And before we even get started, this work is being presented by me, but there's definitely a lot of people involved, and I wanted to give some credits to them. So they're listed there at the bottom of the slide. Next. So today I wanted to briefly touch on first the DART mission overview to kind of get situated, the DRACO instrument on the DART spacecraft and its different components, the DART image pipeline, how it all comes together, and how the flight software imager application is involved in the DART image pipeline. Then we'll dig into the real meat of the presentation, the testing campaign. So how we went from a software in the loop testing through the hill to end-to-end, closed loop simulations, integration and testing campaign when the spacecraft was coming together, and then the launch campaign and DRACO commissioning in space. And finally, we'll touch on some of the lessons learned. Next. So what I wanted to make sure that I get across by the end of the presentation, hopefully, is to not only show the process of developing a DART flight software application, but also share ways to effectively transition flight software from theory to practice to eventually a product, right? Because I think as a developer, at least as I was starting out, it was kind of difficult to capture in my mind the idea of flight software as a product, which it essentially is, right? It provides an interface to the spacecraft, a way for an operator or a tester to control a spacecraft. And so as flight software developers, I think there's a real importance in understanding that concept. Next. So let's start first by digging a little bit into the mission. You can go ahead to the next slide. So the DART launch period was November 24th. This slide is a little old, but on November 24th or November 25th, depending on where you were on the world, the DART spacecraft was sitting on top of a Falcon 9 from SpaceX in California, and we launched that day this mission that is funded out of NASA, the Planetary Defense Coordination Office. And the idea is to create or to test this technology called the kinetic impactor, which really is just another way of saying, if we want to defend the planet because an asteroid is coming our way, can we just simply push it out of the way by crashing something against it as hard as we can? And that's what DART is, right? DART is our little kinetic impactor, and it is aimed, it's targeted at a binary asteroid system called Didymos, which is composed of a larger asteroid, Didymos, about 780 meters in diameter, and then Dimorphos, its moon. And we decided to crash the spacecraft against the smaller moon. And it wasn't only to make it harder, but also because we can actually better understand the impact of the mission by checking on the change of the orbital period of the Dimorphos moon around the larger asteroid. And you can envision that, this asteroid is about 6.8 million miles away from Earth. So the spacecraft needs to autonomously guide itself to the target, right? To Dimorphos. There's not a human sitting on the spacecraft, right? Thank goodness. And there's also not enough room for us to be controlling the spacecraft live. So it definitely needs to be an autonomous spacecraft. And that's where things start to get interesting. So if you go to the next slide, the DART spacecraft has a lot of different technologies, very cool, like ion propulsion engine, rollout solar arrays, but I want to focus on the DRACO telescope, which is DART's single eye. And so let's dig into it. In this picture here, there's also another one that we'll briefly touch on, the autonomous navigation smart nav, right? And we'll touch on that on just a little bit, but really our focus is on the single eye of the spacecraft DRACO. You can go to the next slide. So typically when people look at DRACO, they think, oh yes, the telescope, right? That's a telescope, but there's a lot more to the DRACO system than just the telescope. So if you go to the next slide, I break these down. The DRACO telescope, it's the actual telescope sitting out the bottom of the spacecraft. You see it there on the top right picture with the DRACO door open, right? And there's kind of a hole there. That's the telescope. And this is what has the mirrors in it and stuff, right? But after that, there's a DRACO detector, which is actually capturing that image data. Further down the line, there's the focal plane electronics, which control the configuration of the detector to configure things like the gain of the detector, what kind of shutter it is, the integration time. And then there's also the DRACO image processor, or what we summarize as DRIP. This is an FPGA on the avionics single board computer, which handles the image processing that does things like compute centroids, calculate identify the bounding boxes of that centroid, the intensity of the centroid. And then there's the instrument telemetry manager, which is the software running on that FPGA. Finally, and most interesting to us in this field is the imager, the flight software application that allows us to interact or provides an interface to DRIP and the FPE. Go ahead to the next slide. So I've kind of grabbed all of those components and thrown them into a single diagram, and that's what we see here. Briefly, the image comes in through number 1, the telescope. The data gets recorded or captured by a detector in number 2. We're constantly configuring and grabbing telemetry from the status of the DRACO instrument through the DRACO focal plane electronics on number 3. From number 3 to number 4, there's a SerDes link where this image data goes from the DRACO instrument over to the DRACO image processor, where that centroiding is going on at number 4 in that blue box in the middle. And then from there, the image data can take 2 paths, and I labeled those as 5. Either it can be recorded to flash, the image data can be recorded to flash, or we can send it over to the radio interface adapter, which then sends it through number 6, which then sends it to the radio on number 7, and eventually that gets downlinked to Earth. So this is kind of just like where all those components fit, right? And flight software is kind of sitting in the middle of all of it. From the imager application perspective, being able to control the FPE through this mission-specific card called the MISC there, as well as just directly to the DRACO image processor. Go on to the next slide. So the flight software imager application contributes to this DRACO subsystem, like I mentioned before, by allowing us to interface with the DRACO image processor through RMAP writes and read transactions over SpaceWire, and it allows us to also communicate once. So usually the RMAP read write transactions are used for actually booting the DRACO image processor. Once it has booted, we can send configuration commands to stream record and set other parameters in DRIP via CCSES packet transactions. And then for the focal plane electronics, we also use SpaceWire RMAP to configure the detector. Something very interesting, if you go to the next slide, is that because all of these operations are very multifaceted, right? Like if I want to boot DRIP, there are certain steps I need to take. That means that I don't want the user to be interacting and having to say, send this command, and send this command, and send this command every single time that DRIP is going to be booted. So the flight software imager application was developed as a finite state machine based application, in which we define states that then can be linked up in a sequence. And we just tell the user, execute the sequence so that you can boot DRIP, or execute the sequence so that you can configure the FPE. And the user doesn't have to be very involved in each step. If we go to the next slide, we can get really started on the testing campaign. So how do all of these things, now that we have a little bit of a base on how everything works together, let's start looking at the meat of the presentation. Go to the next slide. So our software, it all starts right with a flight software developer, and our group decided to work in a software in the loop environment, completely containerized at the time with Docker. And the idea was that we could have a flight software application running on a PC Linux container, communicating to a testbed software container, running a testbed software FPE emulation. This testbed software FPE emulation would allow us to update the register space, just like we plan to do on the real spacecraft, maintain that register state, and then provide feedback in, in 1 Hertz telemetry, just like we expected from the real spacecraft. There were some things like, power control and things like that that we couldn't control, but it gave us the opportunity, the SIL environment gave us the opportunity to start testing out the commanding and telemetry pipelines, how flight software itself was routing messages around, how the testbed software was responding, whether we were interacting in a commanding and telemetry aspect with the FPE correctly. All that could kind of be sorted out. And also very important, it is the first time that as flight software developers, we're thinking about what kinds of tests we want to run, what exactly leads to a successful test versus a failed test. If you go to the next slide, in this testing journey, the next phase was, well, the DRACO team eventually told us, the DRACO instrument team eventually told us, we have an FPE hardware we can now test with. You don't have to work with the emulation anymore. Let's actually test some of this stuff out with the real hardware. So we took the SIL and the testbed software team provided an FPE interface application, which could actually from the container talk to the FPE hardware sitting on the instrumentation table, right? Like where it was being developed. We just set up a laptop with our SIL, tested that same command and telemetry handling, and we started to notice some reuse. The same Ruby tests that we used for the Cosmos ground station to do our testing, those same Ruby tests could now be used to test the commanding and telemetry pipelines with the actual FPE hardware. So as a flight software developer, this is really where you're getting to interact most with the instrument team, right? When you're talking to them and you're starting to also realize what the instrument team wants to be able to see, what kind of telemetry is important to them, how they want to visualize it, all that kind of stuff you're taking in as a flight software developer to think about what at the end your application should be able to provide. Go on to the next slide. So the next step was naturally, let's put all this on a test bed, on a hardware test bed, and let's replace some of these emulations with real hardware. So the first things were an engineering model DRACO image processor, an engineering model focal plane electronic. Can we repeat exactly what we did on our SIL? And at this point, we're still very early in the development phase. So the flight software developer is constantly, or I guess we as the flight software developers are very involved in that. I test something, it breaks, I got to redeploy, try it again, that kind of feedback interaction. But if we go to the next slide, that's where things start getting interesting. And I think as flight software developers, where we really, at least I've learned that it's really important to be involved, right? In this idea of end-to-end testing. Where now we're trying to test the pieces of the hardware themselves, and flight software is seen as just a product for the first time. It needs to provide an interface, and it cannot get in the way, but provide a window into what exactly is going on in the hardware, if something does go wrong. And so what we did in this first end-to-end test was the DRACO image processor in that blue box can generate an internal image pattern. So we decided, let's test that image pattern from DRIP through the radio interface adapter to the radio and down to the ground. And now we're also including ground software folks. How does that image data get reconstructed? And you might think, well, that's a ground software question. Why does flight software need to be involved? Well, if something is wrong with that image, or something is wrong in the header of that image, or whatever it may be, there may be ways for flight software to kind of be able to rapidly identify that problem, right? And if there are ways to do that are not exposed, this is where you're starting to realize, as a flight software developer, I need to expose those things. If we go to the next slide, the next step was then we've tested one half of the image pipeline. Let's test the whole image pipeline. So now let's let's use the internal pattern generator in the DRACO focal plane electronics, flow that to DRACO image processor, and then follow the same path as in our previous test. And what's really cool about this test is not only that you're testing new things like, SERDES, our actual UART connection through the mission specific card on the lower right corner, but also you're using this two-box pattern now, which means that its intensity, its bounding boxes. So you can start to test in this holistic approach. Is the DRACO image processor looking at identifying the centroids as I expect them, identifying the intensity, and reporting that back to the guidance and control system, which is then going to be, and that smart nav on those smart nav algorithms, which are then going to guide the spacecraft towards the target. So again, at this point, the flight software imager application is literally just the means to an end, right? We're trying to stay out of the way, but again, being very careful about learning and soaking in what kinds of information folks are paying attention to. And it really gets exciting when you go to the next slide and we take a look at, first we replace the DRACO FPE we replace the DRACO internal FPE generator, right, that pattern, with the DRACO detector, and you get that first image through. At this point, it's just like as a flight software developer, it's just an exciting part of the process, right? To be able to see how your application kind of configured all these different components and made this pipeline happen in one way or another. In the next slide, we take a look at the next step in the testing campaign, which is the closed loop simulation process. We replace that detector because with a render camera emulation. And the reason for doing that is we want to be able to test the entire loop during the terminal phase. So we want to get an image. DRACO image processor processes the image, identifies centroids, sends those back to the smart nav algorithms. Smart nav algorithms detect the target that they want to follow, and then the GNC, the guidance and control system, will either change the attitude of the spacecraft or perform certain maneuvers in order to hit the target. So if we click, that's a video there on the lower left. If we can click play on that video, and what we'll see is the DRACO image processor has the ability to download 1024 by 1024 images, as well as 512 by 512 images. So on the left, you see that bounding box kind of jumping around as we approach Dimorphos, or this RCE generated Dimorphos. And the tracking, right, is being done real time in this closed loop simulation. We're doing all this through a configuration that was done at the very beginning of the operation through the flight software imager application. And something else that's very interesting is now you're starting to really pay attention into what people are looking at, right? Like this is a spacecraft. It's a very complicated system. So people are going to be looking at radio telemetry, power telemetry. They're going to be looking at autonomy state. They're going to be looking at DRACO, but they're not going to be looking at DRACO at the same level that you're looking at DRACO, right? And you start to learn, if you're involved this late into the testing of what Imager is doing or what your application is doing, you start to learn what things are important to you and what things are what the operator is just looking at because they have so many things to worry about. In the next slide, during the integration and testing campaign, if you could click next one more time. During the integration and testing campaign, I actually had the opportunity to be a test conductor. So I got to sit on the chair, sending commands up to the spacecraft, and I got to feel the pressure and excitement both together of kind of operating an entire spacecraft. And I realized, even as an Imager flight software developer, I just didn't have the time to be paying just attention to my one application's telemetry, right? There's a lot going on. And so it gave me an opportunity to see a flight software application as a product and what exactly it is that the operator wants from an application and from flight software as a whole. They're thinking about, they have a spacecraft sitting in front of them at this point, right? Because it's the integration and testing portion of the campaign. So they're looking at the spacecraft and they're thinking, I want to boot drip, or I want to configure the image pipeline. They're not looking at it thinking about the finite state machine state 1, 2, and 3 didn't execute correctly. I don't know why, right? Like they're not thinking that way. And so it really provides, to have this experience and be involved this late, it really provides the experience of, as you're developing a flight software application earlier in the mission, what kinds of things you need to think about the operator looking at, and which ways to scale up, like if there's a failure, how do you report that to the operator in a way that's easily available. How do you report certain failures as warnings and certain failures as critical? These needs immediate attention. So that was a great experience, and during that time, I got to write a lot of different testing scripts that later on in the mission became really instrumental. And I think as a flight software developer, getting to help the DRACO instrumentation team to develop these testing sequences was very rewarding, because not only are you using your application to do these higher level configuration things, but you also really understand, like if you're doing checks, for example, if you perform an operation and you're doing checks, you don't just check, is the configuration correct on the DRACO image processor or on the detector? You're also checking, did my flight software do exactly what I expected it to do? Did it configure everything exactly how I expected it to? Was there, even though I'm in the right state, did flight software report some sort of failure, right? And you're kind of thinking about it in a different way, and in a way that doesn't necessarily concern everybody else, right? Like, essentially, you know a little bit more about what the flight software is actually doing than everybody else. So later in the mission, that becomes instrumental. If we go to the next slide, the launch day arrived, right, November 24th, and again, we're sitting on top of that Falcon 9, and it was time to launch. And that morning, again, one of the scripts that I helped write ran on the spacecraft to do one final check. Does everything look fine? And if you play that video on the left side, that is the moment that the DART spacecraft separated from the Falcon 9, and we got the great opportunity of seeing that real time thanks to the SpaceX live footage. So just very incredible moment. But that's not where it ends, right? Because in the next slide comes the part about now your software is in space, and you're gonna run. Now your software is in space, and you need to configure DRACO and open its eye, like DART's eye, for the first time while you're in space. And this diagram at this point, right? I've gone over it 1,000 times, so it becomes very familiar. But now we're in space, and I tried to trick you, right? By kind of, it's the same exact diagram, but if you look at the top left corner of that image, it no longer says testbed. Now we're sitting on the spacecraft, and now we're sitting, we're actually downlinking images from space. But you've done this 1,000 times before, and as a flight software developer, you're sitting there at the console, right? And you know, because you've been in their place, you know what the Mission Operations Center is looking at, you know what the operator is interested in, and you know that perhaps it doesn't include what you're looking at, so you know what to look at. You know what the instrumentation team is looking at, you know, because you've been there, right? You've done those things. So now as a flight software developer, you realize what things are really important from your perspective, and how to chime in from a completely different point of view without having to repeat information. It even clears up the communication channels, right, during the commissioning process, because you kind of just understand what different folks are looking at. So you can go on to the next slide. And that's the first image from space that DART captured. To us, it was beautiful. To me, it was my wallpaper for a while. But then I replaced it with the next slide. We got an opportunity to do star calibration, M38 starfish cluster, a lot more stars, just to kind of make sure that everything was working properly. And it is. So it was very exciting. So I'm running out of time. I got 30 seconds, so I'll close on the next. If you go 2 slides forward, just some closing remarks. I hope that I was able to convey the importance of just understanding what it is your application is doing. If it's interacting with an instrument, understanding that instrument, how it's used, who the end users are, the operators on the operating it with the spacecraft in space, or the INT team, or the DRACO instrument team. And then I think also understanding that flight software development shouldn't stop at compiled C, right? There's a lot of other ways to that a flight software developer, I think, is critical in the way that we visualize data, and the way that we understand what other folks want to be looking at, and the way that they want to be commanding the spacecraft. So I'll close out by just on the next slide, thanking everybody that was involved with the mission, NASA Planetary Defense Coordination Office, the APL, the DART team, all the software teams, DRACO, INT systems. Just And finally, the Flight Software Workshop Committee for giving me the opportunity to present. So I don't know if there are any questions or if we have time for questions, but.
Unfortunately, we don't have any time for questions. I think we'll move some of the discussion over to Slack, but thank you so much, Luis. Really great presentation.
Thank you.